Ready? Good morning. Timekeepers tell me it's 10:30, and wow, I have a big booming voice in this place. It's exciting. Good morning. My name is Dimitri Williams. I am an assistant professor at the University of Southern California, but I'm here today wearing a slightly different hat as a, I suppose, business guy. I'm going to tell you about some pretty cool tools today, talk about data leveraging, talk about all kinds of stuff. My background is in social psychology. I deal with the psychology of individuals and communities, and with my research team, I've been working on large-scale data set analysis for the last few years. Some of the stuff I'm going to tell you about today is sort of best practices that we've learned over that time, and how to instrument it, and maybe how to think about how these techniques would work in other games as well. I'm a long-term gamer. I've been obsessed since playing Archon on my C64, and probably like many of you, I'm surprised that you can make money doing these things and you don't have to pay to do them. So let me start off with the basic idea behind modeling and predicting behavior and data use. Everything essentially boils down to a relationship between two variables, something you can find and something you want to be able to find. Your Y variable is the outcome. In science, we call that the dependent variable. You just call it the thing you're interested in. And the question today, and I'll show you a few examples of this, obviously, the question for you will be, what is it that you want to know? What is the outcome variable that you want to know? The obvious cases should be things like why people quit your game, who's going to spend money on your game, who's having fun in your game, who's cheating in your game, who's exploiting your game, who is winning your game. It doesn't really matter from the point of view of the algorithms and the methods we use what that outcome variable is. And that's going to vary by company and by application. But you will, I'm assuming, think of these Y outcomes. The question for us as analysts is, how do we predict that Y variable pretty well based on what's going to happen, what has happened, and what we think will happen, and how confident are we in the results? That's what the basic talk is about here. I'm going to focus on the case of churn as a way of exemplifying this, because it's the model that we spent the most time on. Churn meaning just simply who's quit your game. So the thinking is basically it's oriented for subscription-based titles for the first half of the talk, and then you'll see a variant of this for more free-to-play models in the second half of the talk. But it could just as easily be for a system where they aren't paying. It's just simply whether they stay or whether they leave. Because there are lots of reasons for you to want people to stay and like your games, even if they're not still paying for them anymore. They may convince friends to come in and play the game. They may buy your next title, etc. So one question I usually ask developers when I talk to them is, do you know how many people you just lost in the last period? And the answer varies from, well, we know it was this, to we actually have no idea. In fact, usually the second answer is the more common one. I have no idea. Here's the business case for doing some kind of more predictive modeling to think about who you just lost and why you lost them. If you're in a subscription-based system, the reasoning is pretty obvious. You have X number of months the person's going to play times the amount that they're going to give you while they're playing it. That's how much that customer is worth to you. So what is your current churn rate? I'm not going to ask for a show of hands, but if I asked you, do you know your current churn rate? I'm guessing that I would have some people raise their hands in this audience and some people wouldn't. Do you know how much money you're going to lose when that person leaves? Do you know how much it costs to get that person in the first place? Because that's the logic that is crucial to deciding whether or not these systems are worth it for you. How much did the person cost to get versus how much are you giving up when they leave? And the teaser here is, what if you could be a little more proactive? What if you could know who's going to leave and intervene? You would then therefore be protecting money leaving your system rather than chasing new money coming into your system. It's just a more proactive way of thinking about it. And if you have some kind of logic or metric to know the likelihood of the person leaving and how much they're worth, well, then you can make a business resource allocation decision about how much it's worth it to you to devote a certain number of assets to keep that person in place. You could base that decision on some logic. Now, typically the cost of customer acquisition is usually 5 to 7 times the cost of retention, but this assumes you have a cost of retention. If you have retention efforts in your system, good for you. I think you're probably way, way ahead of the curve. I don't think most firms do. But if you do you understand that ratio? Do you know the value, and do you know how many resources you're putting in compared to how many people you're going to keep with those resources you're putting in? So my suggestion to you today, the big picture thing, is stop thinking reactively about that's who I just lost. And I'm going to show you some tools to think proactively about, here's how I can keep them, or to know who I can keep. There are several techniques available to do this, and these are things that are pretty well known in social science and computer science. but they haven't necessarily been applied to systems like this before. Some of the ideas that we have in here are cribbed from the cell phone industry. Some are from traditional data mining from the retail market. But very few of them have been done at this scale, and they certainly haven't been done for big socially interactive systems. And that's what makes games a little bit different than, say, recommender systems on Amazon, is you're actually looking at relationships within people within a system. And that social power and that social networking power is something I'm going to spend some time on today to explain to you. But there are also some fairly traditional tools here that we can use. These would come under the heading of regressions, which some of you are probably familiar with, and flavors of regression, but also some beefier tools that come under the heading of machine learning. And there are several different big algorithms. Most of these, again, are pretty well known, but haven't always been done at this scale or in this kind of application. So let me tell you a little bit about social networks and why they matter. This is a book that came out last September, Connected, by Christakis and Fowler. And what it really is a very nice layperson's explanation for the science of social networks. Social network science has been going on in some shape or form for about 150 years. But really only in about the last 10 years has it gotten legs, has it gotten a lot of traction, has it gotten a lot of results. The problem was there wasn't data to test the models. It's really hard to find data not only of people, but of how people interacted with other people. It turns out that those data are actually very easy to get out of game systems and very hard to get out of the real world. There's a notable exception where in upstate New York, the authors were actually able to find a data set that went back 2 generations for a small town called Framingham, where they were able to track who knew who and who had influence on who over time. And you may have seen some of these results written up in Wired or the New York Times Magazine. They tracked lots of things that spread through networks. What you have here is a graph of thin people and fat people. The green nodes in the social network are thin people, and the yellow nodes in the social network are fat people. You take them at time 1, and then you move to time 2, and you see if there are any changes. So you can probably get a little visual sense that this graph is a little bit different than the previous one, right? Here is 20 years before. Here's 20 years after. Now, your first reaction is, wow, Americans are fat. Well, okay, we already kind of knew that. And they're certainly fatter than they used to be. But the interesting social phenomenon here is that the fatness spread through the network contagiously. That is, the fatness was not random. People who were fat became fat if their friends had been fat. And if you had only looked at them and their diet and looked at them as individuals, you would never have the inference that they had been acted upon by someone else near them in the social network. It turns out that lots of things spread through the social network in this way. Obesity, happiness, depression, smoking, losing weight. The green dots actually will propagate through a system as well. So we like to think that we are masters of our own destiny and that our individuals and our systems are autonomous units and we can watch them and predict them. But there's a huge amount of what we call variance explained that comes from social influence. That's a really key thing to make sure that needs to be put in models. So what does this look like in online game data, for example? These are data from an online virtual world that we've been studying. And we have been looking at who quits a game and why they quit. Now, you guys aren't probably trained social network analysts, and there are a lot of things that such people could pick out by looking at this, but even a person looking at these graphs for the first time can notice some trends. You have a big thing in the middle, and then a bunch of little things around the outside. That much is obvious. What that tells you is that some people in your system are heavily socially interconnected, and people on the outside are not socially connected. If you see around the edges, you have isolated people, who we, in our very scientific way, call isolates. And you have groups of 2 people or 3 people together, who we call dyads or triads. Now, it turns out that the extent to which you are connected in these groups has very strong predicted power on whether you quit or go, independent of everything else. Like, you can have a really crappy time in the game, and if you're really heavily socially connected, you're still not going to quit, and vice versa. So knowing the connectedness power matters a lot. These visualizations are really nice ways of kind of getting a general ballpark sense of it, but there's, of course, a lot of math and Greek letters going on in the background. I don't want to, scare everybody off. I'll show you, look, science. There's some science going on here. Here is and those of you who are taking pictures, this will be on the GDC Vault. I always think it's odd if you're taking pictures of slides on the screen. Or give me your card. I'll send you the deck. It's got to have better resolution than your cameras. It's got to. you get data in the background that explains what's going on in big picture trends in this thing here. This particular graph is highlighting a finding at the bottom. You probably can't read it in the back, but what it says is that when predicting who's going to quit based on network signatures and structures and patterns, people who are isolates are 3.5 times more likely than people who are in a network. In some sense, this is a, well, duh kind of a result. Of course, people who are connected are going to be more likely to stay in the system. But did you know the extent of this? I didn't. And when we ran these data in several iterations, we find some bigger picture indications of how important social networks and stickiness are to staying and quitting. So the players have a 65% chance of quitting the game if they are solo. This is also kind of impressive that 35% of players won't quit and are solo, right? They're happy to be alone near other people in a social system. That's kind of odd if you think about it. But compare that to the people in this biggest network, say that big clump in the middle, those people are only going to quit at a rate of 5%. So if you're thinking about how to keep people, one obvious inference here is that, wow, you want them to get together. You want to think about systems and incentive schemes to make people play together. Because it turns out the people are the stickiness more than the game mechanics, which is maybe not what everybody wants to hear in a developer crowd, but happens to be the case. This is what the math shows us. Now, this also tells us that there are some people in networks who are inherently different than others, should be thought about differently, should be treated differently. And one of the things that you want to do, whether you're in business intelligence or in development, is to understand how you can find these people, how you can label these people appropriately, so that you can then have a conversation about what to do about them potentially differently. There are some people in your networks who are simply more important than others, not by virtue of how much money they pay you, not by virtue of how good they are at your game, but by virtue of the fact that they keep other people there. As you saw in those network graphs, and we'll see a little bit more when we zoom in on them, there are some people who we say are more central into a network. They're the hubs. Other people who are off on the spokes, okay, if they leave, you lost their money or their patronage and they're gone. But if you lose one of those hubs, there's a good chance you're going to lose the people who are connected to them. That makes them more valuable. And if you had only looked at them in a straight-up matrix-based approach, you would never have seen that social connection, and you never would have realized that their value was not just them, but their influence on other people. Now, that is an obvious way of saying that some people are more important to keep. The same thing actually happens in reverse. There are some people who have negative influence in your systems and who look like they are valuable to you, but in fact are costing you because they are driving people out. In the same way that those big green dots showed obesity spreading through a system, you can have a serious asshat in your system who is driving other players away. I'm pretty sure that everybody here has either seen one of those people or been one of those people in some kind of online network game. Xbox Live with the voice enabled. It's not hard to find these folks, right? Well, if you could find them, you would maybe want to deal with them differently. And if you could figure out how much they're worth and how much they're costing you, it might change your relationship with those people. Maybe the solution is to get rid of them. Maybe the solution is to group them with each other. Maybe the solution is to change the mechanics that they happen to run into in the game. Oh, gee. There are lots of ways to think about this. But the idea is, let's see if we can find people. So here's an example of us going in and trying to find a particular class of people. Most folks here are probably familiar with the gold farmer issue, the RMT issue in online virtual worlds. We know from talking with the customer support folks that the gold farmers essentially follow a organizational model that we find in the drug industry, where you have people who bring the product on the left, who then give the product to a central person in the middle, who then disperse it to the customers. This is sort of a well-known drug mule model, and it happens to be the exact network signature that you would find among gold farmers as well. Now, again, something you would not find if you weren't looking at the social networks rather than the individual's behavior. Because if you're just looking for that guy in the middle, I mean, his characteristics are keeps getting lots of money and then gives money to other people. But if you flagged everybody in your system who got a lot of money and gave it to other people, you would get a lot of false positives. But if you found people who had this pattern here, who were always getting it from the same people and then always giving it to different people, that's a signature that doesn't take place in your regular game mechanics in most game systems. So what that means is you can go in and look for this signature in that network. And those are your flags. And in fact, what we did was we started with the list of people who had been banned. We went back in and we looked at their network signatures, and lo and behold, this is what they looked like. We then went in and looked for the signature and found a list of people who had not been banned. Lo and behold, these are people who probably should be banned. So this doesn't mean that this generates a list and here's the people who you automatically boot out. But what it does is it delivers you a list of needles rather than the haystack. So your starting point for your enforcement efforts or your follow-up can be far more efficient and with a higher degree of confidence. And you're starting at the point of perhaps you could explain why you just got all these, resources and then you did this. And you have a lot of ammunition at your disposal. What's kind of also cool about this is that if you track these trends over time, you actually get to look at your population like a game warden. You get to not only find out what they're doing, not just from the big picture, they're coming, they're going, they're churning, they're whatever, you actually get to follow their social structures and how those change over time. This is a 6-month slice of data. The trend line, the wiggly line there, is actually banning enforcement activities, number of accounts who were banned. And the two other lines show the social network signatures of the people in the population. And there is a complex story going on here, but the short version is they are reacting to the enforcement activities and trying to change their activities. But they can't change their activities entirely because they still need to do the fundamental task of acquiring the gold and giving it to the consumer. They can bend, but if they break, they're broken, so to speak. You can, of course, use these tools to find good people in your network. There are good network signatures to find and to identify and even to reward. It just so happens that we figured out the science of doing this by learning how to catch bad guys, which is, frankly, a lot more fun. So let me run you through a few of the other more vanilla models that are it takes some explanation, but are perhaps a little more intuitive to use than the social network approach, which takes some getting used to. It took me a few weeks to get my head around the implications of the social network stuff. A logistic regression model, or usually logit for short, is a model where you throw a bunch of variables into the system to try to predict something. So again, we're back to that what X predicts what Y kind of mentality. You can have lots and lots of X. You have to be careful about which X you pick, and there are some mathematical things to worry about, but frankly, that's what you hire guys like us to deal with. What each of these things, the numbers next to these variables are the influence that particular variable had on the likelihood of a person quitting. So, for example, character gender meant that the person was, if they picked a female character, they were 29% more likely to quit in this particular game. Now, some of these things are very actionable and obvious. Some of them are more obscure. Almost all of them require a conversation. What they do is, though, move the conversation from who left to conversations about why they left. So you can then talk to your development team and say, well, what's going on with gender, or what's going on with number of rare items harvested, or what's going on with number of centrality, or whatever. And usually what I find the conversation is, what the hell does that variable mean? Like, you've got this big data set and nobody knows what these variables are. So usually the step one is, let's go find out what the heck that thing means. A second, and I think equally powerful tool, is a rule set model or a decision tree model. This one happens to be called the JRIP model. And what this does is it gives you a sequence of if-then parameters for why a person is about to leave or is likely to leave. It is a very similar kind of approach. It's just a different way of thinking. And I find that some people are better tooled either structurally in their organizations or individually in their own kind of way that their brain works to work with a logit model versus a JRIP model. There's no kind of right or wrong here. In fact, sometimes some of these models are slightly better than others. And I'll show you how to kind of take the best from both in a little bit. But what a rule set model does is it establishes a bunch of variable rules in if-then scenarios that tell you the likelihood of the outcome. And again, the outcome I'm still talking about right now is likelihood of quitting the system. So here is a bunch of if-then parameters. If the number of rare items harvested, whatever that means, is less than or greater to 33, and total days played is less than or equal to 606, and this triangles thing, which don't worry about it, don't look behind the curtain, and number of rare items is less than 1, then the likelihood of quitting is that Of about 1,000 people, or a little over 1,000 people, 864 people who met this condition quit. And only 182 people who met this condition stayed. That's a pretty big percentage of the people. And in fact, that's why this rule comes up number one. Again, you might not know what these variables mean, but now you want to know very badly what these variables mean. Now you're going to go have a conversation and figure out what the hell that is. And it's probably going to generate some discussions, hopefully, with your dev team. I hope. Number of triangles, by the way, is a social networking meter or metric. But there are, of course, lots of ways to think about these things. You could think about it over time. You could think about it by location. You could think about it by rule set. You could think about it by coefficients. And what occurred to us kind of early on was that it's a lot of information to take in, and not everybody wants to look behind the curtain. Not everybody wants to think about these decision tree algorithms. Sometimes what you want is the simple snapshot of things. Here as it happens, this is people leveling over time, and this is days of account creation, so about 2 years worth of data. And you can see, for example, that early on you have a lot of people leave the system in their first day or two, and then the likelihood of them leaving as they play is lower and lower. And then right before the end, as it increased, there's a higher likelihood of them leaving again once the account age reaches a certain time. So there's another way of slicing the data, and in this particular case it happens to say, here are some points where your player population time-wise is particularly at risk. Maybe it's because of something in human nature. Maybe it's because of something in the game path or game mechanics. It's worth having the conversation about. So now I'm going to show you a set of tools that we've developed to dashboard this process to make it easier. My company is called Ninja Metrics, frankly, because I think ninjas are cool. And our snarky name for our engine is the Katana engine. At first I just thought that was cool because ninjas are cool, and so katanas are cool. And then I realized, it slices data. That was a little geek humor, but it worked for us. What this dashboard is doing is showing you a nice presentation version of all of that math that was sitting in the background, and stuff that might be a little more actionable and accessible, and something you could use to explain to your boss or to your wife if she were kind enough to listen about this. So let me run you through some of the functions. This is this is live. This is working right now. But this is an engine that was developed about 8.5 days ago, so it's not perfectly polished. This is happened to be the timing that it was ready right before GDC. The science behind this is very much happening right now. This is latest and greatest stuff. And as I mentioned before, a lot of these techniques and tools were known but weren't done on this scale before. My team used to do analysis of 10 megabyte, 20, 30 megabyte files. We'd be studying, like election returns or something, and we'd throw it into SPSS or SAS on our systems, and we'd do some stat ninjutsu and write a report and publish a paper, and everybody'd be happy and people would get tenure. And then we started getting gigabyte-sized files, and then our machines ran a little bit slower. And then we started getting terabyte-sized files, and our machines started to look at us funny and say, that's not going to happen. It turns out when you run some of these models through these systems, some of them are single-pass algorithms. They're calculating things. Some of them are recurring algorithms. Like a multiple regression, you're running the data changes, you run it again, you run it again, you run it again, you run it again. Well, that's fine for a 10 meg file. But what happens when you're looking at the economy table from a virtual world and your row has 1.2 million entries? There is no computer that can handle that. And trust me, we are using supercomputing arrays at some of the really the most badass supercomputing facilities in the country in academia. This is high-end stuff. So we had to rewrite algorithms that could do things at that scale. And then we thought that was really cool. And then all of a sudden, Zynga has 8 billion customers, and we're thinking, okay, data sets are about to get even larger still. So now we're building a cloud array system and retooling algorithms to go up to the 100, 200, 300, 400, 500 terabyte level to do that again. But however big the data is, the dashboard sits at your company and is either looking at data locally if you can handle it on your own, or is sitting on our remote servers where we have the capacity to handle it, and it's through a web interface. The idea is if you want to look behind the curtain, you can, but here's a nice easy tool for you to see what's going on. So step one is just simply, all right, let's take a look at the population. Let's see who has stayed and who has gone. And so on the left here you see expansion packs, and you can see who's joined, and you can kind of see the churn pattern, and you could look, well, this was obviously good. Obviously, this expansion didn't go over very well. Something bad happened, and something good happened here. And then kind of a quick snapshot of the kinds of players in the system. And again, I told you earlier there are different kinds of people in your system. In ours, we have flagged people who we think are at risk, and I'll show you how much they're at risk and why you should think about them differently. And then people who are not particularly at risk, and then people that you want to get rid of, and then people who are just sitting around. You can go back in time with some of these tools, that's the obvious thing, and look at past performance. Here is a system, and you can, of course, sort these things and look at how much money you lost when they left, and then export this data off and give it to your BI guys and say, we lost this number of people and it cost us this much money, and therefore here's the case for some kind of intervention technique. So the dashboard is specifically intended to put some kind of monetary value on these people so that you can make actionable items within your own company to justify the resources it would take. But if you know what they have done, you can also know what they're going to do, and that's where things get a little more interesting. Because if 100 people with the exact same characteristics as the player you're looking at quit after 5 months, you can be pretty sure that the player you're looking at is also going to quit after 5 months. The more people you have, the more confident you are in the prediction for this next person. The more similar they are, and the more number of cases they are, the more confident you are in your prediction. Now, your prediction is never going to reach 100%, because a player who is perfectly happy with your game is at some point going to get divorced or get hit by a bus on their way home. And they're going to quit, and you're never going to know why. There is always some data loss. Therefore, there is always the risk of the false negative and the false positive in these systems. But you're going to find levels of predictability. They're going to range from 50, 60, 70, up to 90%. And that's going to let you make some kind of intelligent decision about how much effort you want to put into looking at this case. Well, it's a 50% likelihood. Maybe it's worth sending off an email. It's a 90% likelihood. Maybe it's worth getting a GM to go talk to that person, or it's worth booting that person, or it's more worth whatever. It's a decision you can make, at least now, based on something, rather than a user report or something you're not entirely sure what to do about. So the way this system works is we classify them in the category that they are, how much money you're going to lose if they go, the methodological technique we use to come up with that number, and the mathematical confidence that number gives you in that particular decision. The next step of this, like I said, this is only a week and a half old, but the next step of this is actually to use what are called ensemble methods that combine multiple algorithms together to make a more powerful one. So for example, if you are using a Logit model and it gives you 80% confidence, and you're using a JRIT model and it gives you 85% confidence, when you put those two things together, the ensemble combined model is always as good, at least as good as the top one. And the bottom one might have been explaining some of the variance that the top one wasn't. So when you combine these two things together, say an 80, an 85, and an 86, your overall confidence might jump up to, say, 88 or 89. That'll be the next column, maybe next week. We'll see. We're working on that. Now, some visualization tools to try to take a look at this. That also gets you thinking a little bit. Standard heat map technology and thinking has been around for a while. It's usually used to think about, well, let's look at the telemetry data from, our first-person shooter and see, here's where people are dying, here's where the snipers are, here's where they picked up the railgun, here's where they did whatever. Those are all dependent variables of different interest. I'm, again, looking at a dependent variable, the outcome variable of quitting. And I'm tying in, where did people go and then quit? So the red points here are places where subsequent quitting was higher. Now, this model can change, and you can change the assumptions. But if I mouse over it here, that people in this instance, the 750 people did something, and obviously there was a lot of quitting going on. And I go down here, and people in this area had 2,500 activities, and there wasn't much quitting going on. Obviously, your gut reaction should be, what the fuck is going on up here? Right? You want to tell your dev team, if these are two instances, for example, and they have equal amounts of people in them, how come everybody who goes this one quits and everybody who goes this one stays? And that should tell you two things. Number one, this instance up top is broken, and you need to go in and look more closely at it and find out what's going wrong. Number two, this one down here is working really well and is teaching you things about good game design in some way. And then here is what we think is kind of the killer app here. I showed you the network maps before of influence. I'm now going to show you network maps of actual account IDs within the system and their likelihood of churning in and out of the system, but I'm putting the dollar values onto those labels as well. And the dollar values that are going to be there are going to show you not just how much they are worth, but how much they are worth because of their social influence of others. Therefore, some people will have low value because they are going to drive others away. Some people are going to have higher value than just themselves because they are the things that are keeping other people in your system. So, for example, these red nodes are people who are likely to quit, and the blue nodes are people who are not likely to quit. I don't know how well you can see this in the back here. I can zoom in a little. This person is obviously not worth $500 to you on their own. This is a $15 a month subscription title, and we probably have pegged this person in the middle here with our algorithm as likely to stay for another 12, 13 months. So, they're worth $150, $160. But if you just looked at their behavior again, you wouldn't get the full picture. You also want to get their influence on others. And the thing is, if they go, past behavior suggests that a lot of those other nodes are also going to go. That's why they are worth more. The same thing can be true in reverse. Some person might be worth less because they're driving others out. Again, what you do with this business intelligence is up to you, but at least now you can make an informed decision and you can say, let's devote resources into looking at what's going on with that guy. Let's make sure that guy doesn't leave. Or you find a group who is entirely at risk and you think, let's prevent them from leaving. Obviously the problem is their leader is about to go, and therefore we know from past behavior that everybody else around them is about to quit. Let's hook them up with somebody else who's not about to quit. Let's build a mechanic in that's going to insulate their social network when it gets this shock. Again, proactive rather than reactive. And it might have seemed like there weren't tools to think this way or to support this kind of thing, but it's there. The math is here now. The same thing could have been done with the gold farming. You could use this to find out, this heat map isn't working right now. You could use this to find out where the gold farmers are sitting as well. And you could look at their particular network activities to find out that you just change the red and the blue values to be farmers or not farmers, and you zoom in and find them and find their networks in addition. So it's just really just different kind of powerful thinking. And then you also could do other data visualizations. For example, some of the data that sit in these systems are over time data. They're what we call longitudinal data. And others are more cumulative or cross-sectional data. So there's a difference between character X has killed 8,000 mobs versus character X killed a spider today. Two different types of data. The cumulative cross-sectional stuff is also very interesting and worth mining. Requires a different mentality than thinking about over time data. But when you have these cumulative data sets, you could set up little visualization tools like this to, take a look and zoom in on a class. And then, if I were to click here, it would tell me the likelihood that people who pick this class are going to quit versus others. You can set the dependent variable again at anything you want. So there are lots of ways to visualize these tools and to set them up to customize to the way you do your process, or you do your work. Somebody's really rocking out in the next room, by the way. I don't know if you guys can hear this. Okay, so now I've just showed you cases where we're doing predictive modeling for cheaters and for quitting, which I think are two fairly persuasive business cases for why this kind of technology matters. But there are lots of other things you'd want to predict. And of course, not just the flavor of the month, but probably one of the flavors of the future is the extent to which people are spending money in free-to-play and monetization-based systems. And there is no reason at all why these same kinds of techniques can't be used to predict who is going to spend in a system like that as well. Because, the models don't care what the dependent variable is. They're agnostic to it. You want to predict spending, you can predict spending. But it does require a little bit different type of thinking because it's a slightly different type of system. And there's a different tool here. And this is where I highlight the work that I'm doing on more of a consulting basis with a startup venture called Turia, which I'm going to talk about. There's a dapper gentleman in the middle of the audience who I'll flag in a little while, and a very intelligent-looking Israeli man here who does a lot of science. He looks kind of intimidating. I don't know. Maybe I'll point him out later. So Turia was just founded and are venture-backed. I think are very proud, by the way, of anybody who attended GameSpeed at GDC, won the best startup. And I think the head of the organization was telling me he gets to take a trip to Atlanta as a result of this. I don't know if he's going to go to Atlanta or not, but I don't think he was expecting this. But the focus here is on increasing monetization in free-to-play games. So just a different dependent variable set. And this is the stuff that I work with them on. The interest for their product is generally around three kinds of major activities: customer acquisition, customer retention, and monetization and virtual goods use within those systems. And much like the academic team I work with, it is a team of expert data modelers and tech entrepreneurs. So in this case, you want to use the data to increase monetization by, of course, extending the length of time that people are playing. If they play more, they're probably going to spend more. Taking advantage of and understanding and tracking viral behaviors within networks like this. Predicting the outcomes by targeting the users with different kinds of marketing, realizing that if you segment the crowd, that you would want to treat some of them differently because they're going to behave differently and react to different things. So the segmentation mentality is such that rather than send an email to everybody or system-wide something to everybody, you do what the retail industry has done, and you start customizing the signals you send out to your player base based on some intelligent segmentation that is in turn based on many of the tools that you've already seen demonstrated here. And of course, the bottom line is to try to get them to spend more money. You can also improve the basic game experience for them in the same way. So we started in this process, again, with the academic research that has this kind of broad framework for segmenting user behaviors. And by using clustering analysis, we saw the data supported a lot of suggested player traits and kind of categories. We assume that each player possesses each of these categories to some degree. They're all going to vary. So if we give them a score for traits X, Y, and Z, you're going to build a profile for each person where they're high on X and they're low on Z and they're high on Q, etc. This is in contrast with just defining somebody as, a competitor and doesn't look at their other characteristics. We're looking at the wide field of things. And again, the target variable here is now monetization, but the system idea is the same, what's predicting it. So I'm going to walk you through a case where we're looking at a particular classification or segmentation scheme, and this happens to be in this game that we were doing the data analysis on, their competitiveness. We found out early on that the competitiveness of the player resulted in lots of good things for the customer. In this case, these are data that come from Bumper Stars, which is a free-to-play Flash-based game run by a company called Large Animal Games, who were very good at opening their data vaults and helping us establish a lot of these techniques. It's important to identify the competitive players in this particular game because they spent more money and they were more highly engaged. And again, there's a lot of sophisticated modeling going on, and if you're curious about this, we'll talk afterwards. I'll introduce you to the serious-looking Israeli gentleman, and you can see behind the curtain if you're into it. So let's take a look at those people who are classified as competitive and see if they are, in fact, different once they've been classified through our algorithm. The competitive folks are the blue bars, and everybody else are the green bars. And as you can see just visually, in every case, when presented with some kind of competitive stimuli, the subgroup we identify as competitive was, in fact, different, so it's a nice test. And they were both better, and they played more. So on the left, you see how good are they. Their scores in the game were always higher. And how often did they play? They played a lot more. That's the graph on the right. In this case, the customer is able to take this information, segment the way he was massaging his customer base, and is able to improve their business metrics and better drive their own internal decision-making systems about how to act and how to treat these customers differently, group them differently, appeal to them differently. So user segmentation in online games is as valuable, if not more valuable, than in the real world because the data that we have here are more consistent and more in-depth. We have more signals than you get, with a similar system through Amazon or Walmart or Sears. The technology is based on the same kinds of thinking that they've had in their systems. We've just got more stuff. Our games generate more stuff. We've got more data to feed into this stuff. So given the pretty negligible cost associated with producing virtual goods, the need to connect players with items that are of interest to them is something that really needs to be, should be, can be intelligently automated in a way that other sectors can't take advantage of. So it's a nice opportunity. Here is the Leaf Node dashboard. This is another dashboard system, but this one is different in its uses internally for your company than the ones I showed you earlier. This particular thing here is kind of a way of looking at the heartbeat of the game, looking at a snapshot of what's going on. looking at what it costs to acquire your players, what it's costing and the likelihood of keeping your players, and what the monetization schemes are like and how well they're performing. So whereas the dashboard, the first system I showed you was here are how people are staying and going and you're turning into the system. Here is instead how much they're spending when they're in there, and here's how they're flowing in and out in a similar kind of way. The nice thing about a dashboard system like this is a real-time monitoring system. So if you can get the data hooks built into your system and work with a firm like this, you can get immediate feedback. And if you can have immediate feedback, you don't have to react to trends. You see them right away. So you can program the system to send you alerts when opportunities or problems are cropping up. And again, there are modules in this thing here that cover these, what we think are these three key baselines. The cost of and getting the user, segmenting the user, and then monetizing them. And each of the dashboards, I'm happy to show these things afterwards. I just didn't want to have the talk go too long. Each of them has sort of a custom interface that's going to help. For acquisition, it's going to allow the publisher to buy traffic probability based on the predicted user LTV. And you're going to be able to use the predicted behavior to target through the customer messaging or notification system or some other intervention. And you're going to be able to use the predictive behavior models to make automated, personalized virtual goods recommendations to the person as well. No more shotgun. Now, brand placement might be a potential killer app. The thinking is that brands and advertisers are just beginning to realize the opportunity that branded items represent in gaming. We don't think this is an opportunity that is on the decline. We think this is where there's a very good chance that things are headed. And then, of course, there's a strong link between the user behavior and the brand identity awareness, and that has great untapped potential. So the ability to discover, target, and quantify new information around the motivations of the brand items can be really invaluable. If you wanted to negotiate something with a brand, if they're coming and talking to you and saying, is it worth it putting our brand in your game, you've got to be able to give them some hard metrics and show yes or no. It's got to be based on something. Otherwise, in the same sense that somebody is buying ad time or putting up an ad on Google, they have metrics, and that's why they'll make that investment. And if they don't, they're just going to make a leap of faith for you. So, the dashboard system here is to show, here's how many people are, in fact, identifying with your brand. Here's how many people are acquiring virtual items that are working that way. And if we can work with them even better, then you can possibly link to systems that allow for outside click-through and follow-up in the same sense that maybe, Amazon gets a referral and knows where it comes from and credits it appropriately. So all those things are possible. So that was a lot of information to take in. I just gave you social networks, I gave you machine learning algorithms, I gave you money-making schemes. There's a ton of stuff going on. The science here is, I think, really exciting. This is all stuff that's come out of academia, but we think has pretty strong commercial application. And it's really malleable. It's stuff that can be adapted for lots of different kinds of games. We're working with some very well-known large-scale free-to-play systems with monetization. We're working with first-person shooter titles. We're working with virtual world titles. This stuff, it's got legs and it can adapt. If you have any questions, I'm going to have question period in a second here, but if you've got follow-ups or you want the deck of slides from me or you want to have follow-up conversations, my email's at the top. And Chethan, raise your hand, Chethan, wearing the jacket, is in the middle of the crowd here from Turiya. We'll both be happy to talk to you. So I think I've left enough time for Q&A. If anybody would like to come up, fire away. Thank you.
Thanks for that great talk. Quick question. For your Katana engine, what kind of data requirements are there that you can actually work with the data set? Is there anything that you would recommend to like a company who's interested to provide certain data, the format of the data? Can you basically work with anything, or how does that work?
Sensitive? Hello? Okay. So the question was, what kind of data do you need to feed into this system? That's a complicated answer, but let me give you the short version of it. Good data. Clean data. The costs associated with instrumenting the system are directly related to how well organized those data were in the first place. I have worked with data systems where we dealt with 28 different databases whose structural formats changed over time. The costs associated with getting those understood were much higher than for a system that's really well organized. So one question you may want to ask yourself is, do you have a data person who understands your data and who has a lookup table? For example, if we get a field which says location equals 7, is there somebody who can tell us what 7 means? Even if the data is clean, we still need the intelligence to know what that means. Now, to some extent, the machine learning systems don't care. But once you get into the why part of the decision making and you're drilling down and trying to understand what these things mean, you're going to need to know what the variables mean. And of course, your models, when you're building them, are going to be more sophisticated if you understand them from the scratch. But the other half of the answer is any data. It doesn't matter. The only thing that might be a little bit different is that the social networking data requires connections between players. So if you can think about data which can incorporate actions or interactions between players, they can turn into those hubs and spokes. So for example, these two players, like in a virtual world like EverQuest or WoW, it's pretty obvious. They traded with each other, they sent each other tells, they're part of the same guild, they went on a raid together, they're in the same party. And you can decide which of those building blocks are most important or appropriate for the outcome variable you're suggesting. So for the gold farming analysis, that was trade data. That obviously makes the most sense. The person-to-person tell data wouldn't be as predictive of gold farming, whereas the stickiness and churn stuff was more built on tell interactions and whether they went off to kill mobs together. But in say, a shooter title, it could be, did you play on the map at the same time? Did you send messages to each other? Are you part of the same clan? And if you can build those hooks into your system, the more hooks that are built in, the better these models are going to work. So cleanliness and understanding it and the ability to put in new stuff all makes these things more powerful. Yes.
Hi. So I work for InView. We built our company on data, much like this, although we haven't really gotten to the point of the social network analysis that you do. So I was very interested in seeing this. One problem we're facing is scale. So your numbers were like, there's 1,000 players maybe churning. So when your data volumes are like 100 or 1,000 times that, have you worked on scaling those kinds of analysis?
So our data have been very large because of time span, but not because of volume. Our algorithms should work on those large ones, but nobody has done that. I mean, we've got a cloud array sitting there, and I've got a team of 25 people, including a bunch of computer science PhD students, who really geek out on exactly that thing, and we want big batches of data to do this. There's no reason it shouldn't work.
All right.
Because it's worked on the volume, but that volume isn't based on time, not on population, but there's no reason it shouldn't work on population as well.
Okay.
Yeah, we're mining 10 terabyte files, so the power's there. Yeah.
Are there any implications in your models to gender or age? Does it span?
Lots. So when I'm not wearing my business guy hat, I'm wearing my pointy-headed academic hat, and we spend a lot of time looking at gender differences for social and cultural reasons and for looking at game mechanic reasons as well. So we've spent a lot of time in particular looking at what makes men and women tick differently in these situations. I didn't mention one important data type in this talk, and that's survey data. My background is as a survey methodologist, and the difference between data from games and data in surveys is the difference between behaviors and attitudes, right? So you can get some inference about what happened and maybe why they left, but you don't know how they felt. If you want to know an outcome like satisfaction or happiness or disgust, you have to ask them a survey question. And that's something we can do and have built into these models as well. Usually you get gender and age data based on the upfront registration process for a game system, and it's usually pretty trustworthy. So you can use that as both a predictor or an outcome variable as well. Like if you wanted to find out how do the women play the game differently from the men. It turns out in virtual world systems that the women play in some ways very similarly to the men, but depending on how they were introduced to the game, they will play it differently. The women, for example, for whom their boyfriends or husbands were gatekeepers into the system, they play in a pretty stereotypically female way. They are killing fewer monsters, they are talking more and hanging out. And you can see that in the behavioral metrics really cleanly. For the women who came in on their own, they are killers, vicious, brutal beasts, right? They are more male than the men. Like you look at their social interactions, they're lower than the men. You look at their kill rates, they're higher than the men. In fact, when you look at the most hardcore players, the really truly hardcore players, the women are like way oversampled, and it's from this really hardcore group. So it was an interesting finding for us academically, but also has some commercial implications in that there is a very hardcore female subgroup which is not like the other girls.
Thank you.
Yeah.
You mentioned social network triangles. Can you elaborate a little bit on what that is?
So a triangle is simply a triad in the system. So if you have within that big cloud of things, I showed you that there were clusters and big components, and that there are isolates and there are dyads. A triangle is just when you've got a pattern where the same three people keep interacting very frequently, and that's, depending on how you instrument this, there are a lot of assumptions and things we could change, that's the main pattern we see for those people. Three people who always play together, or who have reached a certain threshold of number of times or number of incidents in the system.
Kind of an opposite question of what was asked earlier about scale. At what point should a small social game company be looking at this type of statistics in terms of segmenting the population? At what point is there enough data to be statistically significant?
It doesn't actually take too much to get statistical significance for big things. It takes more numbers to get significance for small things. So a psychologist who's running a test who doesn't know how big the difference is going to be tries to get 30 people in the treatment group and the control group of an experiment. The logic being that usually most things you can find with 30 versus 30, it's going to show up as statistically significant in the sense you're suggesting. It really depends on, if the difference is male versus female, you don't need a big sample. You're going to be able to classify with, 5 and 5. And you're going to be sure that you didn't get the results by chance. But if it's the difference between, somebody who is in a great mood versus only a really good mood, it's this small little thing, you might need thousands of people to do it. But the traditional academic models, you're looking at a few hundred data points, not the million table rows we're talking about. The science for finding difference is actually based on much smaller populations. And so the techniques work fine at small scales. When I talked about the building up of the algorithms and the computer science guys getting excited by it, this is an obstacle as much as an opportunity, but we're building on a smaller scale platform which has been around for decades, which works really well. So it's fine. Yes.
I was wondering, what dimensions do you use to recommend virtual goods to users, game players? To segment the users, basically segmentation.
You want to field that, Jathan? Apparently after. Yes. Mm-hmm. So the question is whether or not we trust people's self-disclosed gender when we're looking at things. So the two data sources that we use are either survey data or self-reported registration data from a system, and it kind of varies. When we're doing the social analysis on the purely academic side, we were actually looking at both. So if they were consistent, and they tend to be, they're probably more trustworthy. But it really comes down to whether or not you trust the data that are gathered anonymously in the first place. I think most of us have kind of the Greg House mentality at treating the patient, and you're not sure if they're going to tell you the right thing. There are lots of errors in data, and they come under the two following categories. One is they just got it wrong. If I ask you in the audience, how many hours of television did you watch last week? You're going to give me an answer that is close, but that is not exact. If the true answer was 8, you might say 7, you might say 9. You're not going to nail it, or most of you aren't going to nail it. So there's noise in the data. And then the second half of the answer is some of you are going to lie because you want to overrepresent or underrepresent those things. But it turns out that when you ask people in anonymous settings, that second error category actually goes down, and you're more confident in it. If I ask you face-to-face, how many hours of TV did you watch last week, you'd be like, I don't watch TV, or I watched 3, when the truth is 25, or whatever. Or that same thing about video games, I don't play video games, But if I ask you online, the answers are pretty good. So we're not particularly worried about the gender issue in particular. The more sensitive things we could ask, like the real test of this, we ask people about their sexuality or their income. And they're giving us answers in line with known statistics for the demographics of the game audience in the first place. So if they'll answer those things truthfully, we're not particularly worried about their gender. Yes? Could you come up to the mic? So everybody else could hear you better, too. For me, I'm dueling with some party going on in the next room.
Hi, are you planning to have a self-serving platform, or it will be mostly through somebody manually we have to interact with to get the data in the system?
I didn't quite catch that.
So, is there a way that a small publisher or a game developer can go to a website and, based on the description of the field, upload files every day or every night, and then they can get the recommendations? Self-serving platform.
You're asking about our business model and how much we charge big versus small customers to do this?
Not only charge-wise, the way it works itself.
Or can it be done?
Yeah.
Well, certainly it can be done at any size. There's nothing about the methodology which says it has to work for massive populations versus small. That's the beauty of something being scalable. As to the kind of features we would build in and how much it's worth to you and how much it would cost, I think that each one of those things would be a separate conversation with different people coming from different backgrounds in the audience. But you'd want to come up with a system where it makes sense to you, where the return you're going to get is worth the cost. And if we sat down and we found out that our cost would be X amount of dollars to instrument it, and your ROI for how much saving based on the population size would be less than or more than that, you'd make a decision about whether it was worth the investment. The idea is that it's based on a projection. You're not guessing in the dark. We'd look at the population and think about the return and then think about whether it's worth it cost-wise for you. It's going to vary. A startup and Zynga are going to have very different business models and philosophies on this and potential savings and potential gains from this. Yes? Oh, can I do this? Can I do this without dealing with you guys? Thank you. I think we have time for one more question. And by the way, I've just been asked by the nice people in the green shirts if you would please fill out the recommendation forms. And of course, write down 5 for everything. That'd be nice. This lets me come back and talk next year and give more results. They really care about the scores, so I'd appreciate it if actually you put down whatever you think is fair. But I'd appreciate it if you'd fill out the forms on your way out. Last question time. So the question was, are there any affordable tools that can do this for small companies? And it's a tough question to ask because the thing I just showed has about 8 different techniques built into it. So you can find some reasonably costed solutions for one of them rather than, say, all 8 of them that will work on relatively small scales. And so for example, if what you want to do is to run logistic regression models, you can buy a statistics package like SAS or SPSS, and those are things that are in the hundreds of dollars. The cost is really going to be more finding the person who knows how to use them wisely and understand their output than it will be in the tool set itself. But those systems are really good for small scale data, and once you get up into the big files, into the gigabyte files, then things slow down. But there are some off-the-shelf stuff, especially for standard statistics. There are a few also now coming out for social network analysis as well. But again, you need someone at the wheel driving it pretty well. There are actually some free packages for some social network systems. The things you'd want to look at if you're going to go online and browse for this, look for Sienna, look for P-star ERGM, ERGM, exponential random graph models. There are a few others. And if anybody is curious about these things, I'm happy you can send me an email. I can refer you to some people who can maybe answer the question better. But again, you need somebody who knows what they mean. That's the thing. I think we're out of time, so thanks very much for the questions. Cheers.